looking at degrees, minutes, and seconds, which is a way to take degrees and split it into smaller intervals, like you could split feet into inches and so forth. So it's actually kind of related to time, which is why minutes and seconds are used, because we use 60ths as our denominator. So 1 minute is a 60th of a degree. A second is a 60th of a minute, or 3,600ths of a degree. Okay, so very, very specific. All right, so what we're going to do is learn how to convert these, and really a lot of this is just what are things that we're going to do on our calculator. So first we need to learn how to type stuff in, and it's all written right here in your notes about how to type it in. Okay, so if you want to go back and look at it, it's all right there. But we'll practice one here. So we're going to type in 53 degrees, 20 minutes, and 19 seconds in our calculator. So I want to make sure first that my calculator is in degrees. Mine is not. And then I'm going to, Colby's here, everyone. For those of you watching this at home, he just showed up. Thank you for your pass, Colby. You're going to be famous now. Years from now, people are going to be like, who's Colby? Okay, so we're going to type in 53 degrees like this, 53. And then you're going to go second. Above the apps button is an angle menu. And there you can see that we're going to find the degrees under number 1 and minutes under number 2. And for some weird reason, TI thought it should be good to put the seconds somewhere else. We'll find that in a second. But we want number 1 right now, 53 degrees. And we're going to type in 20 seconds by going back to second angle, hitting number 2. Oops, what did I do there? Second angle. I'm doing number 2. And then to do 19 seconds, we want to go alpha, and then above the plus sign, this thing is not being very nice to me today, and above the plus sign is your seconds. And all you simply do is hit enter. And there's your degree to the nearest, whatever you want to round it to. We're asked to go to the nearest thousandth here. So this is going to be 53.383339 degrees. Okay. I have here, here's what's really happening. Your calculator is making this calculation here. They're taking 53 and adding it to 20/60ths and adding that to 19/3600ths because of the relation between minutes and degrees and seconds and degrees. All right. And you could do that by hand. It probably takes just as long to type that in as it does to type in the other stuff, but that choice is up to you. Now, if you want to convert back to degrees, minutes, seconds, like if I had this measure right here that I am showing on my calculator and I want to go back to degrees, minutes, seconds, it's pretty simple. You just go second, go back to that angle menu, and number 4 says, hey, put that thing back in degrees, minutes, seconds. So hit number 4, and it says you want to take that answer and put it back into DMS, and there it is. Okay, so what I'd like you to do is try finding out what 34.843 degrees is in degrees, minutes, seconds, or in DMS. All right, so you're going to have to type that in. And you should get 34 degrees, 50 minutes, and 34.8 seconds. So that's new concept number 1. I don't know if you've ever seen degrees, minutes, seconds before. Have you? Okay. Now, really, we could do anything that we normally do with degrees. We could do more specifically with DMS. And every once in a while, I think they throw that sort of stuff at you in the homework. But a lot of the DMS stuff is just converting back and forth, so you have an understanding of what it is. New idea number 2 in our trigonometry unit is bearings. Okay, and I actually, we started this section yesterday. And I said this yesterday as we went through our notes. I went through a lot of stuff that our notes won't actually cover. until section 2 and section 3 because I wanted to throw everything at you that you could remember from Algebra 2 and kind of gauge where we were at. And unfortunately, I didn't get to the new stuff, and that's what a lot of the homework from last night was. So if you didn't finish much of last night's homework, that's on me because I didn't really tell you what bearings were or what DMS was. So you have that excuse for last night. Okay. All right. So another way to measure an angle is using bearings. Bearing is a angle measure from due north. So it's used a lot in navigation. So I put this little compass on here. We're going to throw a couple of measures on here just as benchmarks. So north would be considered 0 degrees. East then would be 90 degrees. So opening clockwise is positive. I'm going to get rid of that arrow because we'll throw a few other things in there. Northeast then would be 45, and I think this is a good one to put in 22.5 because then what that tells you is every click there going around this compass on those ones that are marked is 22.5 degrees. So for example, we know that this is 180, this is 270 right here, and then all the way back to north would be 360. But if we wanted to know, for example, what, let's say west-northwest was, that would be 22.5 degrees more than 270, or 292.5 degrees. Did I do my math there right? I'm on cruise control right now. Hold on. Looks good. Okay, so you could give any of those measures that are shown up there in a degree bearing. All right, so let's take a look at this here. Actually, yeah, let's do example 6 here first. It says, the captain of the tourist boat Julia out of Oak Harbor follows a bearing of 38 degrees for 2 miles and then changes to a bearing of 47-degree course for the next 4 miles. Draw a sketch of this trip. Luke Weatherall is now here. Thanks, Luke. All right, so we've got, I'm just going to put Oak Harbor down here. There's where our boat is leaving from. Okay, now if he were to go on a bearing of 0 degrees, that would be due north. So I'm just going to put like this thing here and say that's 0 degrees. He's going to go on a bearing for 38 degrees, which means from due north, I'm going to go down 38. So kind of almost 45. And he's going to do that for 2 miles. So I'm just going to guess, or not guess, but I'm going to just say that's 2 miles right there. All right? I didn't really hit my arrow all that way, did I? Okay, so that's, I'm just going to say that that's 2 miles. I don't put that there to show that I'm representing 2 miles there. Now from that spot, he's going to go on a bearing of, so I'm going to call that 0, and you don't have to put that 0 degrees. I like to do that for this example. But now he's going to go on a bearing of 47 degrees. Should be a little bit further. So my angle is going to be a little bit sharper. But I think the other important thing is that we try to make that second line twice as long as the first line to also give some distance here, right? Because he went 2 miles the first time, 4 miles the second time. This is where he's going to end up. Does it look like about twice as long? Pretty good. Maybe there we go. And then I'm also going to throw these in here. This was 37 degrees, or 38 degrees. Shoot. 38 degrees. And then this one was 47. A bearing of 47 degrees. Okay. All right, so let's convert a bearing of 140 degrees into a radian measurement here. So let's find out what 140 degrees is as a standard angle. So I'm just going to do this. I'm just going to draw a bearing of 140 degrees. This would be 90. All the way down to the negative y-axis would be 180. So I'm going to be, how far short of that y-axis? 40 degrees short. Actually, let's do this way. Let's look at a reference angle here. What would my reference angle be right there? How far past 90 did I go? How far past 90? got to answer something. You guys are being recorded right now.
Oh, 140 minus 90 is 50.
Okay. Colby hasn't even woken up yet. He's sleep answering.
I can use some of my eyes closed.
I think, did we accidentally say that this was 50 degrees here? That we were short of the y-axis? Because that wouldn't be 50 degrees, that would be 40. Maybe we said 40, I don't remember. I'm sleep teaching. All right, so our reference angle back to that x-axis would be 50 degrees, okay? And we want to use that because, or we're going to use that to help us figure out what this would be as a standard angle, okay? What would this be as a standard angle going all the way around here? Well, I'm 50 degrees short of that 360, so this is 310 degrees in standard form. When they ask us to do a radian measurement, that means in standard form, not as a bearing anymore. Okay? To make that a little bit clearer. So now what we need to do is convert 310 to radians, which we did yesterday. Go pi over 180 and cancel out the degrees and a factor of 10. We have 31 over 18, 31 pi over 18 radians. How are we doing with that? Okay, now some applications here. Well, that was a sort of application. Another application that we're going to be using in this section is angular speed in relation to what's called linear speed. Linear speed is something that you're used to. Linear speed is how fast something is traveling one direction. That's the speed that you're used to. And angular speed is how fast something is spinning. We could give that in a few different ways. We could call that revolutions per time, revolutions per second, revolutions per minute. You've heard of RPMs before. That's an angular speed. Okay. Or we could have even radians per minute, radians per second, radians per unit time. So some things to keep in mind here. There are 2 pi radians in one trip around a circle, right? Let's call that 1 revolution. In other words, we just wrote in words the formula for circumference, because circumference is 1 revolution. All right, so this says a turntable rotates at 50 revolutions per minute. What is its angular speed in radians per second? Okay, pretty important idea here. You always want to start with the rate you're given. I'm going to do some conversions here. A lot of dimensional analysis type stuff here. So we have 50 revolutions per 1 minute is what we're given. We want to convert that to radians per second. Okay, we'll take care of the time later. Let's take care of getting the revolutions to be radians. So what we just set up above is pretty important. How many radians are in 1 revolution? 2 pi. That's huge, because then we can just say 1 revolution, so I can get those revolutions to cancel out, is equal to 2 pi radians. Revolutions are gone. Now, if I were to stop right now and multiply across, I'd be in radians per minute, but I want to be in radians per second. So our last conversion is going to be from minutes to seconds. Get those minutes to cancel out. And now we are in radians. Oh, don't do that. Uh-oh. Brother, all this is working just fine if you showed up. All right. Now we are in radians per second, which is what we want it to be in. All right, so now we have to, we can simplify a few things here. I can cancel out that multiple of 10 between the 50 and the 60. So we're going to have 10 pi over 6, or I can simplify between the 2 and the 6. So we're, looks like 5 pi over 3. radians per second. Let's find out what that is as a decimal, though, too, here. Go ahead and type that into your calculator. Find out what 5 pi divided by 3 is. And notice how I called it 5 pi over 3 radians per second instead of saying 5 pi radians per 3 seconds, because we want a unit rate. I think you should end up getting 5.2, I'm going to round to the thousandths here, 36. Does that sound correct?
Yeah.
5 second pi divided by 3. Beautiful. Radians per second. Good? All right. It says radius of a car wheel is 13 inches. I'm going to stop right there. If the radius of the car wheel is 13 inches, one revolution would be equal to the circumference, which would be 2 pi r, or 26 pi inches. Throw that in there too. Okay? We can use it. We can use any combination of that as a conversion factor. They want to know how many revolutions per minute the wheel is making when the car is traveling 40 miles per hour. So just like the last problem, and this is something that a lot of students struggle with because it's the last thing that's given to you, you still want to start with that rate. That 40 miles per hour is what you're given. That's what you want to start with. You don't just start with the 13 inches or the 26 pi inches because it's the first thing that we found. You always want to start with the rate. So we have 40 miles per hour, and we want to go to, what do we want to go to? Revolutions per minute is what we're looking to find. So we're going to have to go miles to revolutions. Well, right now I can go from inches to revolutions, right? So I got to get miles into inches first so that I can go from inches to revolutions. Does that make sense? All right, so let's go from miles to inches here. What would be my first conversion to get from miles to inches? Miles to feet, so I have 1 mile. And yes, you do need to know this. 5,280. You know a good way to remember that? No, seriously, does anyone know a good way to remember that? Because I have none. Just remember it. Just remember it. Okay. Luke has it written on the inside of his calculator. Don't do that. He's like, oh, wait, that's kind of a good idea. All right, so you got 5,280 feet per 1 mile. We want to go to inches, though, so let's go 1 foot down here, 12 inches. Good job, Luke. On top of it. All right, so right now, I'm going to start canceling things out so I can find out where I'm at. Miles are gone. Feet are gone. Right now, I'd be in inches per hour, right? I want to be in revolutions per minute. So we need to get, let's stick with the inches to revolutions here. And this is the kind of the main one here. The stuff that we just came up with right here is going to help us out in this conversion. We know that 26 pi inches, and I'm putting it down below because I want to get rid of the inches, is equivalent to 1 revolution. So now we get those inches to cancel out, and now we'd be in revolutions per hour. Our last conversion is to go from hours to minutes. 1 hour, 60 minutes. Look at these guys cancel out. All right, there's a lot going on here. So simplify however you want to. Here is the one thing I will warn you about. I know I'm in revolutions per minute right now because everything else canceled out. I'm just going to write all the values that we are left with right here. 12, and then down here we have, I'll just say revolutions, and down here we have 26 pi and 60. Don't forget that pi. Bless you. Okay, don't forget that pi. Here's what I will warn you about. If you just want to type this on your calculator, I'm absolutely fine with that. If you want to simplify some stuff there first, go for it. But make sure you put this stuff in the bottom in parentheses, otherwise you will be multiplying by things you shouldn't be. So I'm going to go 40 times 5280 times 12, and I'm going to divide that by, now make sure you put this stuff in parentheses, 26 pi And please use pi and not 3.14 times 60. We should get about 517.13 revolutions per minute. Good? All right. We're going to stop there. We might look at that example 10 tomorrow as kind of a warm-up example. But we're going to stop there, and we're going to start with our second section. All right, so at the very least, what I would do as you look at this table is fill out your big three. All right, and again, I'm going to try to do it without, and I'd like you to try to remember these without your right triangles. Knowing the right triangles is great, because we're going to use those in applications too, your special right triangles. But knowing these is gooder, better, more useful at times, all right? Because if you only want to find a single value, it's kind of nice to just be able to rattle off a single value. So sine and cosine of complementary angles are always the same, so sine and cosine of 30 and 60 are 1/2 respectively. I just remember that the square root of 3 over 2 is the other guy. Sine and cosine of 45 are both the square root of 2 over 2, which means that tangent's 1. And then it's these other tangents that get a little ugly, but they're not too bad. And if you want to keep going, you can flip all of these to get the next three. That's a pretty easy one. This is the ugly one. And then don't forget that these are corresponding. All right, rock and roll. Here we go. So a lot of this is, even simpler, I think, than some of the stuff that we did yesterday. Got a little spot for you to write this guy. You have your right triangle definitions of the three trig functions there. The thing that SOHCAHTOA actually represents. And then we have our reciprocal ratios. Just so you remember what they're actually called, we have cosecant, secant, and cotangent. And they are reciprocals of sine, cosine, and tangent, respectively. So there we have that cosecant is 1 over sine. We could also say, if you were dealing with a right triangle, that cosecant of an angle would be, if you're dealing with a right triangle, if sine is opposite over hypotenuse, cosecant would be hypotenuse over opposite. And you could do that for the rest of these too. Flip those right triangle definitions. But I'll let you do that on your own. Let's take a look at, and again, I could have probably just handed these notes to you and said, hey, try this problem. These are pretty straightforward. These are like ACT type problems that really stem from some of the stuff you did in geometry. So you want to find all 6 trig functions of an angle. Please understand that everything we are dealing with right now are acute angles, meaning that they come from right triangles. So it is okay to use SOHCAHTOA, all right? So we obviously need that missing piece right there. What would that, or how would you find that side? Yes. Why did you say that? I know why you said that. What did you think it was? But he thought it was a 30, 60, 90, right? But it's not. It'd be cool if it was, but it isn't. The Pythagorean theorem. All right, so we've got 21 squared plus something squared, if you want to call it x, equals 29 squared. $441. Is it 841? Yeah. So side is 20, isn't it? Awesome. Now it's literally just a SOHCAHTOA here. So we have, make sure you know what your angle is. It's right there. So your opposite is 20 over 29. Cosine would be 21 over 29. By the way, what do those two values always have to be? What are these two values always going to be? Think about it. Sine and cosine are always going to be what? Your sine and cosine values. Okay, let me ask you this. What is this number always going to be compared to the two numbers that are in the numerator? It's always going to be bigger, because isn't the hypotenuse always a bigger side, the biggest side? So what are these two values always going to be?
Smaller than 1.
Smaller than 1. They're always going to be small. By fractions, I think Luke meant that they were smaller than 1. All right, so tangents all over the board. And if you think about it, you guys, look at our graphs of sine and cosine. Don't they bounce between 1 and -1, right? Never goes above 1. Now, we're not going to have negatives here because we're dealing with right triangles, but it's always going to be between -1 and 1. All right, tangent, that's all over the board. Okay, it could be small, it could be big. If you remember what the graph tangent looks like, it looks like this, and it's got some asymptotes, right? Because it's undefined at odd multiples of pi over 2. All right, now we got to go numerator over numerator, 20 over 21, or you can go back to your picture and go opposite over adjacent. Now we're just flipping all these. Cosecant and secant are always going to be bigger than 1, right? Because you're always going to be flipping two values that are smaller than 1. Questions at all? All right. So, probably won't finish these, but I just want to get to this one here so you see kind of the idea is that you need to come up with your own triangle. If you're told that this, and it doesn't matter how you draw it, it's just got to be a right triangle. But if you're told that the sine is 1/3, you are being told that the opposite is 1 and the hypotenuse is 3, and you need to find that other side. So that other side is going to be, with a little bit of math, you're going to take 9 minus 1 and take the square root, right? Square root of 8 is 2 square root of 2. So that just came from Pythagorean theorem. All right, so our sine this time is going to be, well, we have the sine. Don't forget you were actually given that the sine is 1/3, so we have sine and cosecant pretty easily. All right, the cosine would be what? 2 square root of 2 over 3. Good. If you flip that guy, 3 over 2 square root of 2, remember we want to rationalize. You just do a little scratch work with that. You're going to have 3 square root of 2. What do you get from that product in the denominator? 4, right? Because you have 2 times 2. Because those square roots of 2 multiplied together give you 2. So you basically have 2 times 2. So we have 3 square roots of 2 over 2. Tangent would be opposite over adjacent. So we're going to have square root of 2 over 4. And then we'd have to flip that to get cotangent. 4 over the square root of 2, square root of 2, square root of 2. We get 4 square roots of 2 over 2, and that simplifies to 2 square roots of 2. Which probably would have been easier if I would have done adjacent over opposite looking at the triangle, right? But math is fun. All right. Last one there that I want to look at. What does it mean to solve a triangle? Find all the parts. So you're going to be given some parts. Go down and fill in what you're given right away. We know C is 90 degrees. We know that A is 5. Oop. Put them in the right spot. I usually use capital letters for my angles. I did this like this because this is how you're going to see it from the book, from the worksheet that we have. So I use the same thing. They're using Greek letters to represent the angles, which is also very common as well. We use theta all the time, right? So you got 90 degrees there. What else do we know? Like beta is 59. If you want to put those up there, that's not a bad idea. 59 right there, 5 right there. Now, a couple of rules. 2 rules here. Make sure, well, this isn't a rule, this is a common sense thing. Make sure your calc is in degrees. Because that's what we're dealing with here. Okay? And then my other rule, and I'm not going to write it because I think you guys used this one from last year, don't use values you've calculated if you can help it. So what I mean is, we can use the cosine of 59 degrees to help us find C. Because that would be 5, the adjacent, over the hypotenuse C. Now remember, you can flip that C and that cosine of 59. Now you're just typing that into your calculator. 5 divided by the cosine of 59. The nice thing is you can just type that all in like that, not close up that parenthesis, you get 9.71 and be happy. C is about 9.71. We're going to round our sides to the 100th and then the angles to the 10th, but the angles we don't need to worry about rounding. All right. Oh, what is A? What is angle A? Yeah, so you can use the fact that those two are complementary. And then we'd use another trig function to find B.